Updates for you tonight. Crews are responding right now to a new fire start tonight in Yellowstone National Park. The ash fire.
Satellites scanning the rugged terrain of the American Northwest recently picked up a startling signal beneath the Earth's surface. Instruments belonging to the United States Geological Survey identified vast channels of molten rock that appear to thread their way from deep under Yellowstone National Park toward the formidable volcanic giants of Mount St. Helens and Mount Hood. For decades, geologists speculated about the possibility of hidden corridors linking volcanic systems across the Cascade Range, but never before has evidence surfaced with such clarity. What was once an abstract model, something confined to academic debates and computer simulations, has now taken on a more tangible form as satellite readings expose the fiery veins coursing through the continental crust. The warning issued by the USGS is not a declaration of eruption, but it is a recognition that subterranean connections exist where few expected them to be so prominent or so extensive. Before we start, smash the like and subscribe buttons for more updates. The discovery highlights the sheer complexity of the geology of the western United States. Yellowstone, famed for its caldera and geothermal activity, has long been understood as one of the most volatile volcanic systems on Earth. It is a hotspot-driven supervolcano, its activity powered by a mantle plume that burns through the continental plate. On the other hand, Mount St. Helens and Mount Hood belong to the Cascade Volcanic Arc, which is generated by subduction of the Juan de Fuca plate beneath the North American plate. For these two distinct volcanic mechanisms to display an apparent link through magma tunnels unsettles many long-held assumptions. It suggests that the crust beneath the region may be less segmented and more fluidly interconnected than previously thought. It also underscores that geological systems do not always conform to human-made classifications, and that the dynamics of Earth's interior often blur the lines between what scientists neatly divide as hotspot and subduction volcanism. The satellite imagery that triggered the USGS alert is remarkable not only for its clarity, but also for the scope of what it revealed. The thermal and gravimetric data indicated channels of molten material stretching hundreds of miles, weaving through zones of weakness in the lithosphere. These are not narrow fractures, but wide, robust tunnels, capable of channeling vast amounts of magma. The implication is staggering. Pressure and heat from Yellowstone's mantle source could find pathways that influence the volcanic systems of the Cascades. Conversely, the tectonic stresses and magma accumulation of the Cascades might impact the Yellowstone system, creating a feedback loop that links the destinies of these distant volcanic provinces. This realization carries scientific intrigue and a sense of urgency, for it means that the behavior of one volcano could reverberate through others in ways not previously modeled. Researchers are now tasked with piecing together the consequences of such an interconnected system. One immediate implication is the reassessment of volcanic hazard maps. Traditionally, hazard zones are defined locally, based on the eruptive history and structural integrity of individual volcanoes. But with Yellowstone, Mount St. Helens, and Mount Hood potentially tied together, risk assessments must expand in scope. A disturbance in one system could cascade, quite literally, into activity in another. For example, magma movement beneath Yellowstone, even if it does not culminate in an eruption, could send pressure waves through these tunnels and influence the magma chambers beneath the Cascades. This would mean that seismologists and volcanologists must monitor the systems not in isolation, but as nodes in a greater web. The scientific intrigue of this discovery also extends to questions about Earth's geodynamic history. How long have these tunnels existed? Are they recent geological formations carved by gradual shifts in tectonic stress? Or do they represent ancient structures dating back millions of years? If they are long-standing, perhaps they have silently influenced volcanic activity across the region for far longer than humans have recorded. Patterns of eruptions in the Northwest, from the violent 1980 eruption of Mount St. Helens to Yellowstone's periodic caldera-forming events, might need reinterpretation in light of these hidden linkages. It could be that these eruptions, often considered isolated, were part of a larger narrative of connected subterranean forces. The technological aspect of this revelation is equally fascinating. The satellites that detected the tunnels rely on a combination of thermal infrared sensors and gravimetric measurements capable of registering subtle variations in Earth's gravitational field. Where magma accumulates, it slightly alters the gravitational pull at the surface, and where heat radiates, it shifts the infrared signature. By layering these datasets, scientists were able to reconstruct the outlines of the tunnels in astonishing detail. This represents a leap forward in remote sensing technology, a demonstration that the hidden architecture of Earth's crust can be mapped without direct drilling or seismic surveys. It paves the way for future discoveries, suggesting that other volcanic systems around the world might also be interconnected in ways humanity has yet to imagine. The human reaction to such findings is inevitably colored by awe and unease. Yellowstone alone is a source of constant fascination and fear, a supervolcano whose eruptions in the distant past reshaped entire continents. Mount St. Helens, with its catastrophic 1980 eruption, lives vividly in collective memory as a symbol of volcanic devastation. Mount Hood, while less explosive in recent history, towers over Portland, Oregon as a looming sentinel of volcanic possibility. The idea that these three mighty volcanoes are bound together beneath the surface transforms them from isolated giants into parts of a single sprawling beast. This metaphor of a subterranean network emphasizes not only geological reality, but also cultural perception, for it alters how people envision the land beneath their feet. For local communities, the discovery demands a recalibration of awareness. Residents of Wyoming, Montana, Idaho, Washington, and Oregon now share a geological destiny more tightly bound than before. Preparedness measures, evacuation planning, and infrastructure resilience must account for scenarios where volcanic unrest is not confined to one area, but potentially affects a multi-state region. While the USGS warning does not signal imminent catastrophe, it does underscore the importance of vigilance. Emergency managers and policymakers will likely revisit protocols in light of this expanded understanding of risk. In the age of rapid information flow, the challenge is to communicate the gravity of the discovery without inciting unnecessary panic. The interconnected magma tunnels also invite philosophical reflection about the nature of Earth's systems. Humanity tends to compartmentalize natural phenomena into manageable categories, yet the planet continually demonstrates that its workings defy rigid boundaries. Yellowstone's connection to the Cascades illustrates that Earth is not a series of isolated mechanisms, but an integrated whole, where processes thousands of miles apart can influence one another. This perspective aligns with emerging scientific paradigms that emphasize systems thinking, recognizing that geology, climate, and even biology operate in interdependent webs. The magma tunnels beneath the American West are a literal manifestation of this principle, a reminder that the planet breathes as a unified organism. From a scientific perspective, the presence of such tunnels challenges models of magma transport. Typically, magma chambers are thought to be somewhat localized, with conduits feeding eruptions on relatively short scales. But the discovery suggests that under certain conditions, magma can travel extraordinary distances through stable channels in the crust. This has implications not only for volcanology, but also for the study of plate tectonics, as it implies that the forces shaping the surface of continents may be more interconnected than expected. It may even offer clues about how supervolcanoes sustain themselves over geologic timescales, drawing on reservoirs far larger than previously understood. There are also intriguing implications for geothermal energy research. If vast tunnels of magma exist, they represent colossal sources of heat that, if ever safely harnessed, could power entire regions. The idea of tapping geothermal energy at such scales remains speculative, yet the discovery expands the horizons of possibility. It raises questions about whether humanity might one day utilize these fiery veins as renewable energy sources, though the risks of interfering with such volatile systems are immense. Still, as the world grapples with the challenge of sustainable energy, such considerations inevitably enter the conversation. At the same time, the discovery deepens humanity's sense of vulnerability. The forces beneath Yellowstone, St. Helens, and Hood dwarf human scale, reminding us that civilizations are built upon a restless planet. The knowledge of these magma tunnels does not herald immediate disaster, but it does reinforce that our control is limited. We can map, monitor, and model, but the ultimate rhythms of the Earth are beyond human command. This humility, uncomfortable though it may be, is vital to living responsibly within planetary boundaries. The scientific community will spend years, perhaps decades, unraveling the mysteries revealed by these satellite findings. Drilling projects, seismic studies, and computer simulations will all play a role in testing the extent and dynamics of the tunnels. International collaboration will be crucial, as volcanologists and geophysicists from around the world contribute insights into the phenomenon. Already comparisons are being drawn to other volcanic regions, such as the connections between Iceland's volcanic systems or the networks beneath Hawaii's islands. The American discovery thus feeds into a broader narrative of planetary science, a global effort to map the unseen arteries of the Earth. For the layperson, the revelation may evoke a more primal response. The idea of tunnels of molten rock threading between mountains conjures imagery both mythic and visceral, as though dragons slumber beneath the ground. This blend of science and imagination is not trivial, for cultural narratives shape how societies respond to geological hazards. Storytelling, art, and media will undoubtedly seize upon the discovery, weaving it into the collective consciousness in ways that influence public perception and policy alike. Just as Mount St. Helens became a symbol in the 1980s of nature's power, so too will the newly revealed tunnels enter the lexicon of American identity in the 21st century. The implications also extend to education. For students learning about Earth science, the discovery offers a vivid example of how knowledge evolves. Textbooks that once depicted Yellowstone and the Cascades as separate systems may soon be outdated. Instead, future generations will learn about the interconnected networks of magma that challenge simplistic models. This reinforces the dynamic nature of science, where discoveries continually reshape understanding and where certainty is always provisional. It also highlights the importance of funding for research and technology, as breakthroughs often emerge from persistent investment in tools like satellites and sensors. In the broader sweep of geological time, the discovery adds another chapter to the saga of Earth's restless crust. The North American continent has been shaped by collisions, rifts, and eruptions across hundreds of millions of years. The magma tunnels beneath Yellowstone, St. Helens, and Hood are but one expression of that ongoing dynamism. They remind us that the continent, seemingly solid and immovable in human experience, is in fact alive with motion and transformation. Mountains rise and erode, magma surges and cools, continents drift and oceans open and close. Against this backdrop, human civilizations appear fleeting, their histories written upon a canvas far older and more enduring. As the scientific community processes the full meaning of this discovery, one fact remains clear: the Earth is more interconnected than we often realize. The magma tunnels beneath the American Northwest are not merely geological curiosities. They are reminders of the vast, unseen systems that shape our world. They bind together iconic landmarks of American geology, Yellowstone, Mount St. Helens, Mount Hood, into a single story of subterranean fire and pressure. And in doing so, they challenge us to rethink not only our scientific models, but also our relationship with the planet itself. This recognition is at once sobering and exhilarating, for it opens new horizons of inquiry while reminding us of the profound mystery that lies beneath our feet. The revelation of magma tunnels stretching between Yellowstone, Mount St. Helens, and Mount Hood not only stuns scientists with its geological implications, but also reshapes how we understand the very fabric of the Pacific Northwest's landscape. What was once considered a patchwork of volcanic systems, each driven by distinct forces, now emerges as a unified framework stitched together by subterranean corridors of molten rock. This recognition prompts a shift in perspective that is far more than technical. It redefines the Northwest as a living organism, its arteries hidden beneath layers of granite and basalt, carrying the lifeblood of fire across states and mountain ranges. The warning from the USGS captures the weight of this realization, for the agency understands that interconnected systems bring complexity that no isolated model could ever fully predict. One striking aspect of this discovery lies in its impact on seismic research. Earthquakes are often the first indicators of magma movement, and for decades, patterns of tremors around Yellowstone and the Cascades were treated separately. Yellowstone's swarm earthquakes were linked to its vast shifting magma chambers, while tremors near Mount St. Helens were tied to pressure building in the Cascades. With the confirmation of tunnels, seismologists must now revisit decades of data and reconsider whether tremors in one area may have subtly echoed in another. A pulse beneath Yellowstone might have registered as a faint vibration beneath the Cascades, dismissed at the time as noise or unrelated activity. The interconnected network offers a new lens for interpreting seismic signatures, suggesting that what appeared to be local disturbances may in fact have been the whispers of a broader, coordinated system humming beneath the crust. The study of volcanic gases also gains new urgency under this framework. Yellowstone's geysers and hot springs constantly vent carbon dioxide, sulfur dioxide, and hydrogen sulfide, painting a picture of its restless subsurface. The Cascades likewise emit gases that warn of magma rising closer to the surface. If tunnels allow pressure and gases to migrate across regions, the chemistry of emissions at one volcano might offer clues about activity elsewhere. Scientists now face the task of developing a regional gas monitoring network that cross-references data between Yellowstone, St. Helens, and Hood. Imagine a scenario where unusual carbon dioxide levels at Yellowstone coincide with subtle sulfur changes at Mount Hood. Under old assumptions, these would be unrelated. Under the new paradigm, they could represent signals of shared magma movement threading through the tunnels. The cultural and historical resonance of such a discovery cannot be overstated. Indigenous nations across the Northwest have long told stories of connections between mountains, framing them as siblings or rivals engaged in constant dialogue. Oral traditions describe these peaks as living entities, capable of anger, jealousy, or cooperation. While science and myth approach the world through different lenses, the discovery of magma tunnels lends new respect to these ancient narratives. The idea that fire flows beneath the ground, linking distant peaks, aligns in striking ways with traditions that saw the mountains as part of one family. For communities rooted in these landscapes for millennia, the USGS warning may feel less like a revelation and more like confirmation of wisdom already embedded in cultural memory. Beyond culture, the discovery compels rethinking of regional geography and geology education. For generations, Yellowstone and the Cascades were taught as case studies of two separate volcanic processes: hotspot volcanism and subduction volcanism. Students learned to compare them, not to connect them. Now, classrooms will need to grapple with a more nuanced picture: that Earth's interior can braid together different geological processes into one flowing narrative. This reshaping of education not only enhances scientific accuracy, but also deepens the wonder of Earth science. A Yellowstone-class trip or a hike up Mount Hood will no longer feel like visits to unrelated sites, but journeys to different expressions of the same hidden network. The presence of magma tunnels also raises profound questions about continental evolution. Continents are not static plates drifting atop molten mantle. They are riddled with weaknesses, fractures, and conduits where heat and pressure reshape their destiny. The western United States, with its dramatic landscapes carved by uplift, erosion, and volcanism, has always stood as testimony to dynamic forces. But the discovery suggests an even greater integration, as though the continent itself is stitched together by fiery seams beneath. This adds weight to the notion that continents evolve not only at their edges, where plates collide or diverge, but also in their interiors, where hidden processes silently shape them from within. Yellowstone and the Cascades are no longer isolated landmarks. They are portals into the evolving soul of North America. Geophysicists are especially intrigued by the mechanics of how such tunnels remain stable over geological time. Molten rock is less dense than solid crust, and it seeks paths of least resistance. For tunnels to persist, there must exist channels of weakness, zones of fractured rock, ancient fault lines, or partially melted material that allow magma to flow without instantly solidifying. The existence of such pathways on the scale detected by satellites challenges assumptions about crustal rigidity. It suggests that beneath the apparent solidity of the continent lies a far more ductile and dynamic environment than previously imagined. In a sense, the crust behaves less like a rigid shell and more like a semi-permeable membrane, allowing deep Earth to communicate with the surface through veins of molten rock. The implications extend to climate history as well. Volcanic eruptions, particularly large ones, inject aerosols and greenhouse gases into the atmosphere, altering climate on regional and even global scales. If Yellowstone, Mount St. Helens, and Mount Hood are connected, then past climatic events may need re-examination. Could simultaneous or staggered eruptions in these regions have contributed collectively to ancient cooling or warming periods? Layers of volcanic ash found across the continent might be reinterpreted as products not of isolated blasts, but of a coordinated chain reaction. This possibility adds a new dimension to paleoclimatology, linking Earth's atmospheric history to the hidden architecture of its molten underworld. The discovery also speaks to the resilience and fragility of ecosystems shaped by volcanism. Yellowstone's steaming basins support unique microbial life that thrives in boiling, mineral-rich waters. The Cascades' fertile slopes nurture forests whose soils are enriched by volcanic ash. If the systems are connected underground, then the flows of heat and mineralized fluids that sustain these ecosystems are also part of a larger exchange. This interconnectedness means that changes beneath one region may ripple outward, subtly altering environments hundreds of miles away. It is a reminder that even the most localized ecological wonders may be fed by distant forces, tied together by threads of fire and mineral carried through Earth's hidden arteries. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Yellowstone magma tunnels? Natural process or looming catastrophic event? We want to hear from you. Thank you for watching and see you next time.